And this one does have a bunch of hands-on on it, so hopefully I'll get people through the last hour and a half here. We're going to talk about modal and signal analysis. This is something that we've been working on in Power World for a number of different years. It actually came out of work that Jim Gronquist did when he was here at BPA with Alex Borden and Bernie Lasser at University of Wisconsin-Madison, my alma mater. And we've tried to integrate it into simulator in a really easy way so that you can analyze signals pretty easily. So the gist of what we'll be talking about is oscillations. An oscillation can be written in the form of a cosine with some constant and with some exponential function where you've got an alpha value there. If you've got omega equal to 0, then this term goes away and it just becomes a constant. It just becomes an exponential function. When we have a function in this form, we talk about its damping ratio, and the damping ratio is defined as given there. The percent damping is just a damping ratio multiplied by 100. The goal is to have signals with positive damping, and that would correspond to an eigenvalue with a negative alpha term in it. So in power systems, we can get lots of different oscillations going on. You can get very high frequency oscillations. Jamie showed some of them when a motor starts up. As an engineer, I always use the term startup transients when I'm talking to people. A lot of times when I talk to non-engineers like my wife, she doesn't know what I'm talking about. But
did you go through the slides for her?
Yeah, she loves looking at these slides. You can get very high frequency, quickly damped oscillations, the so-called startup transients. In a power system, you can get frequencies on the range of 1 to 5 hertz, which tend to be associated with local plan oscillations. Inter-area oscillations tend to be a little slower, 0.15 to 1 hertz. We can get slower dynamics like the automatic generation control dynamics, or you could get subsynchronous resonance on the order of 10 to 50 hertz, something that we don't analyze in simulator. And I showed this one earlier. That's a classic oscillation that has negative damping associated with it, and that's what we want to avoid. Richard showed a waveform where, when you showed that waveform, I thought that'll be so easy to analyze and get the damping on it and the frequency. That's what we're going to be going through here, is to make sense of a waveform like this, or even a waveform like that, or waveforms like this. This is the oscillations that occurred during the August 14th, 2003 blackout, particularly the ones that occurred in there. But in doing this analysis, we are assuming that each component of the waveform has a constant frequency. So if you've got variable frequency, which a little bit of this is variable frequency, that would be a little bit harder to handle. Okay, so what's very common in doing a dynamics run, transient stability run, is to get a frequency, and this is 60 hertz, and this is, I think, like 59.8 hertz, and you get something like that. It's very common to see. Now when I look at that, I think, oh, that's so easy to decompose into its modes. And we'll show how you can easily decompose a response like that into its modes. This tends to be, we'll talk about ring down analysis. There's some event, and then the system rings down and settles out. What we won't be talking about too much here is analyzing more ambient noise and looking at frequency and ambient noise. That's not something that we do currently, but we might be adding it eventually. When you want to do analysis of power system modes, and the modes are just the different frequencies that occur with their damping. Previously, we would use small signal analysis, where you had a small signal package. You'd have a model, you'd linearize about operating point, you'd calculate the eigenvalues, and you would gain information from those eigenvalues. Power World does that for for single machine infinite bus situations. And we use that commonly in dynamics. But PowerWorld doesn't do a general purpose small signal analysis. So it just looks at the individual generators. Rather, what we've implemented is kind of where the industry is going, is to do more measurement-based modal analysis. That is to say, you have some measurements, maybe they're from phasor measurement units in the real system, or they're from a study package like PowerWorld. How do you make sense of those?
That was correct, Jamie, thank you. I was wondering, since a lot of these are slower frequencies, 0.4 hertz and whatnot, do any of the other assumptions in the simulations come into play where, all of the slow stuff was assumed constant for the stability? So, I mean, would that alter?
Not that slow stuff.
Yeah,
Oh, okay.
Yeah,
Oh, okay.
the slow stuff that we assume constant, we were just talking about this over break, is let's say you want to run out a study not for 20, 30, 40 seconds, but you want to run it out for 60 minutes or something. What would you run into then? Then you start needing to model things like how do the LTCs respond? An LTC, it's going to look and say, I've got a low voltage. As long as it stays low, or if it comes back within range within 30 seconds, I won't do anything. That's slower. Yeah, but that wouldn't come into play here for the most part. Okay, so we're going to talk about ring-down modal analysis. There we take the system and we kick it somehow and watch how it rings and do analysis on the rings. There's different ways to analyze a disturbance. The oldest is the Prony approach, which goes back to 1795, surprisingly. It was popularized in the power group, or in the power community by John Hauer and friends in about 1990, I believe. Yeah, that's Prony.
Yeah, BPA folks.
Was that you guys?
Yeah.
Yeah.
So now we're going to go on and say how that wasn't very good.
We don't use Prony. I mean, since then there have been a lot of techniques that have been developed, and they're surprisingly good techniques. They weren't necessarily developed in the power community, but they were something that we can utilize. So regardless of technique, the goal is to represent the response of a sampled signal as a set of exponentially damped sinusoidals, or what we would call the modes in the system. So this is an example where you have a signal, kind of where we started, 60 hertz, it falls off, and then you get some recovery. And what we want to do is we want to take the original signal, which here I've drawn in black, and create a reproduced signal, which is just the sum of these exponentially damped sinusoidals. And here I've shown it in red. And the graph shows that we can do this pretty well. If the black and the red line are on top of each other, we're doing pretty good. And in this example, it took 6 sinusoidals to match the response of that waveform. So the idea of all these techniques is to approximate a signal, let's say y org sub t, by the sum of other simpler signals, and we'll call them the basis functions. Usually they're exponentials, but you can also do linear and quadratic functions. Then we quantify properties of the original signal by looking at the basis functions. The approaches are based on sampling the original signal. So all of these work by sampling a signal. So what we will do is we'll think of a vector y as consisting of m uniformly sampled points from the original signal with some sampling value of delta t. And this will get hands-on in just a second here. I'm just giving you a little bit of the math, which probably not everybody cares about. But I have to sample the signal, and then I'm trying to reproduce those sampled points. And we're only matching the sampled points. That's all the algorithms know about, are the sampled points. What we will then look at is how good are we doing, and we'll calculate something known as the error or the residual at each point. If we add up all the residuals, we get a metric that quantifies how well we're doing. And the algorithms seek to drive this to 0. Okay, Power World has a couple ways to do this, but I'm only going to really show you the one that works the best here today. The approaches that we have can be used with either one signal or multiple signals. Before going on, I should mention a consequence of the Nyquist-Shannon sampling theory, and it says if we want to see frequencies at a particular value, we need to sample the signal at twice those frequencies. So if you're looking at a signal and saying, I want to see things that are 5 hertz or below, I have to sample that signal at 10 hertz. And that is just a fundamental requirement. Sampling shifts the frequency spectrum by 1 over t, which can cause frequency overlap. And this overlapping of frequencies is known as aliasing, which can cause a higher frequency signal to appear to be a lower frequency signal. So if you sample too slow, you can get aliasing going on. And this is an example that I grabbed from Wikipedia. Say you've really got a high frequency signal shown in the red there. So it's oscillating at a high frequency, and you're sampling it just at the points there. Those points also look like a much lower frequency signal. Okay, and that's a consequence of aliasing. It doesn't affect us too much in what we're doing, because usually we can sample at high enough frequency that we don't have problems detecting what we want to find. Okay, so in Power World, we try to make this as easy as possible. We used to just have 2 ways to get access to this tool, but now we have 3 ways to get access to it. If you look at add-ons, now next to the transient stability stuff, there's a little add-on called Modal analysis. On the transient stability form, you can get access to it, and you can also get access to it by right-clicking on the transient stability or plot case information display, and I'll show that in just a second. So let's go ahead and open the case B3_CS_undamped. So it's that one right there. This is talk 8, but it's in the talk 10 directory. So if you open case, it's in the talk 10 modal analysis. It's the first one here. Click on the transient stability, and this is a 3-bus case modeled with Gen CLSs. So a Gen CLS in this case, I don't have any damping in it. I'm just going to put on a self-clearing fault at bus 1. So I'm just going to put on a very quick fault. Rather than faulting it for 0.05 seconds, just fault it for 0.01 seconds. So it's just to get the system oscillating. So I'm going to change that to 0.01. And then I do run transient stability, and I get a plot of the machine speeds at the 3 generators. So the generators are oscillating with respect to one another. We just gave it a little kick, and now they're bouncing around a little bit. There's growing oscillations here. This is a bit of numeric instability because these are classical models, but we don't have to worry about that too much right now. But we're going to say and look at that and quantify what frequencies are present there. If you look at the blue graph, you might think there's just one frequency there and it's growing. It's negatively damped. But if you look at the green one seems to have a more complex behavior to it. The green one is associated with signal 3, and it's got, you know, amplitude that's going up and down. So it's a more complicated signal. in simulator, the way you get access to modal analysis is if you go to results from RAM, if you right click on one column, it doesn't matter which column, go down, right click and go down, modal analysis, go down to modal analysis, all columns. And then,
I'm sorry,
yeah, so on the results from RAM, right click anywhere to get this local menu, and then get modal analysis, all columns. Got it?
and, okay, right click. Sorry, I'm having trouble catching on, my computer restarted.
Oh, okay.
So, analysis, bulk one.
That brings up the modal analysis form. This is a form that if you're me, you like to have topmost. If you're Jamie, you like to keep it contained within your window. Again,
We're working on encapsulating all this stuff into the next version of Simulator 2, so. My whole goal in version 22 is no one will come in here,
come in.
into this document. We're gonna simplify it. Anyway, I'll show it later.
Jamie's working on automating this, which there's good reasons to automate this, but you never want to totally automate it. So
Correct, yeah, you'll always
be able to come in here. If you want it topmost, just go up to the Power World icon and change it around. It doesn't matter much for me. When you do modal analysis, you can do it either on all your signals or a subset of the signals. And later on, I'm going to show how you can do it on thousands of signals at once. Right now, let's just do modal analysis on one signal, and the signals are listed here. The bus 1 speed, bus 2 speed, bus 3 speed. If we include it in modal analysis, this is set to yes. Toggle the first two to no, and that's going to say just analyze signal 3. When you analyze a signal, you have to tell the software, when do I want to start analyzing it? When do I want to stop analyzing it? Time in seconds. So this is a signal, and we're going to look at that signal and sample it. And what is the maximum frequency that we're interested in? And it's going to sample it at twice that maximum frequency. So here it starts not at time t equals 0, but by default it'll start at after the last event. So we put on this little fault, so we're going to start after the last event. So just 100th of a second in. Just take the default of 5 hertz and an end time of 5. Then you go up here to the calculation method. Just use the matrix pencil method and click the do modal analysis button. And what it did is it just analyzed the signal, and through some magic that we'll talk about later on, that is not total magic.
It feels like magic.
Yeah, it does feel like magic. It said, hey, in that signal, you've got a component here that is a 2.236 hertz mode with a damping of minus 0.95%, and you've got a component that's 1.513 hertz with a damping of minus 0.613. Okay, so it just figured that out for you. So that complicated waveform has been broken up into some other ones. There's also one that has 0 frequency. This is just kind of a linear offset on the curve because it's got 0 frequency on it. Okay, hold that right there. So we did that. We went through that. Now, I like to verify what we did. So we allow you to get a lot of information about what you just did. One way to get information about what you just did is if you go to this signal here, the third one that we calculated, and right-click on it, you get a local menu, so you select it, then right-click. Go to the second one down, which is Show the Signal Dialog. this shows information about the signal that we just analyzed. And it says, what is the original value for the signal, what is the reproduced value, and what is the difference? Okay. Let's plot the reproduced versus the original. So to do a quick and dirty plot, if you just use your left button and grab those two columns, then right click, you can do the set toggle columns and go plot column, and there you get a plot using our famous cyan color, which I don't like, so we'll change that to black, and I'll make the scale like 3 here, and then I will plot it. And what I get is the original signal is black, the reproduced signal is red. And they are practically on top of each other. That's the magic. Okay. You can see there's a little bit of black there, so it's not a perfect match, but it's a pretty good match. And you might say, well, yeah, I mean, those are classical generators undamped. It's not that hard to do. And admittedly, this is not that hard to do on these signals. It's a 3-generator system. It's only got really 2 main modes in it, but we captured them. So those signals, we've now quantified them and said what frequencies are there and what is the damping. Okay, that was a simple signal. Let's make it a little bit harder signal. Let's go back into transient stability and go, you can keep the modal one open if you want, or you can close it. Go back into transient stability, go to simulation, and what we're going to do is we're going to change when we apply that fault. We applied the fault at time t equals 0 and cleared it 1/100 of a second later. Let's change that to applying it at time t equals 2 and clearing it at 2.01, and then still running it for 5 seconds after the fault. So we're going to run for a total of 7 seconds. So change the end time to 7. Okay, everybody got that? The fault comes on at time 2. So we're going to run flat for 2 seconds, put the fault on, again clear it after just 1/100 of a second, give it a little kick, then watch it oscillate for 5 more seconds for a total of 7 seconds of simulation time. Got it? So we run it and that's what we get. Okay. Maybe you should close this and reopen it. Yeah, because it would not update the signal. Okay, so we're again going to do modal analysis on the signal. So go to results from RAM, buses. Oh wait, these are generators. Generator. And you see the speed there. Again, select one column and do modal analysis, all columns. Everybody there? Okay, again, we're just going to do one signal initially, so click the include here to know. Okay, it is saying do the modal analysis from start time of 2 to an end time of 7, 2.01. It looked at the simulation and said, hey, your last event was at time 2.01, just do from 2 to 7. If we did from 2 to 7, we would get the same results. But let's do something that we shouldn't do, and that is analyze that signal from 0 to 7. So go ahead and click 0 to 7, then do modal analysis. And it's given it the old college try to take a bunch of sinusoidals and match that signal.
Got
And-
8 of them.
What?
It's got 8.
Yeah, now we've got 8 modes here. Okay. We're again gonna do the same thing where we do the show dialog, show signal dialog on the third signal, and I'm gonna plot these two again. Eventually we hope to get like built-in plotting here, but it's the crude stuff right now. I'm gonna again change the color that I don't like.
I'll show it later, Tom. It's mostly there, actually. I'll show it.
Great.
It was done last week, so Tom hasn't seen it.
So, I think that's a pretty good reproduction of that signal. We took 8 sinusoidals and we added them together and we got that. Not bad. But did we want to do that? No, I mean, we didn't want to do that. We did not want to do that. We should have started at the time it suggested, which was 2.01, and just did the ringing down part. So with modal analysis, the results that you get depend a lot on the signal that you give it. Or actually, it's not just the signal, it's the part of the signal that you give it. So if you're wondering what part to give it, don't give it this flat part, because it will do what you tell it to do. Okay, but I still think that's a pretty cool reproduction. Not bad at all. Okay. So you can, yes, it's damped functions is what we're doing. This is a general signal analysis technique. When you get over this modal page, you can load in PMU data if you want. You can load in ComTrade data. It's just looking at signals. Now, there is a coupling between if a coupling exists, it'll take advantage of that coupling between the model and the signals, but you don't need that. So it's a general tool. And that's what I've been saying to PowerWorld, is I've been saying this is a general tool that can be used with PMU data, whatever you want it to be used with. So it's a general tool. All right, so let's open the case B3 Gen ROU. So in this one, I just took the Gen CLSs and replaced them with the Gen ROUs, which have damping involved. I've got some exciters in there. I got a TGov1 governor. Again, we'll run the simulation for 7 seconds with the fault occurring at 2 seconds. The modal analysis will automatically pick up when to do it, but of course you can override that if you want. Okay, so close that. Okay, so I load it, I go to add-on, transient stability. I run it, and there's our plot right there. Okay. We could get results from RAM and do the same thing as before to show the modal analysis page. Okay, so if you want to do it like that, you can. Modal analysis, all columns. Okay. Another way to do this is modal analysis has been promoted to an add-on. I got that right before when we taught this class in fall. So if you want direct access to this, which is just an application, you can click on that there. Okay, you don't have to go the way that I went. And this is useful in some situations, so I'm gonna go and get it that way. It's calling up the form that already has the data in it. We have different ways that you can get data into this application. That's specified up here. The none existing data is the approach that we're using here, where we're just pulling data out of the results from RAM. A good way to group curves that, or signals that you can bring in here, is to get them from a plot. So if you want to bring in plot data, if you click from plot, then it lets you see the plots right here, and it will bring in data from the plot. So then you just type just load signals, and it will load those signals in from a plot. This is useful if you've got a bunch of plots defined of signals you want to analyze. Just a convenient thing to do. There's other ways where you can bring in data in ComTrade. We might support CSV, but right now, one of these formats is a CSV format. But if you brought in external data from a ComTrade file, we could directly load that in as well. Okay, so now let's analyze it. We'll pick the start time, which is the time of the last event, go out to 7, we'll sample it at 5 hertz, or our maximum frequency is 5 hertz, we're going to sample at 10 hertz. This is a small system, so let's go ahead and reproduce all 3 signals. So it can handle a single signal, or it can handle multiple signals. Just click the Do Modal Analysis, and now it reproduced all 3 signals simultaneously. And it said, I've got in there, I've got that mode, I've got that mode, I've got that mode, and I've got that mode. Okay, so it picked up those from analyzing the 3 signals simultaneously. Now, the really slow frequency modes, if you look at the signals, so I'll just show I guess I'll show a plot of the signals. Modal analysis is just looking at this part of the curve, and it's seeing something that looks like that. It's thinking that's a long, slow oscillation. Okay, so it's got a mode that is a very slow mode. Okay, that one we can ignore. Okay, we're really more concerned about these oscillations going on here. That's why it got that long, slow mode in there, and we only are seeing part of that mode because that mode is slower than 0.1 hertz, and we only looked at the signal over 5 seconds, so we only got like half of that, and it really doesn't exist.
Is there an option to ignore modes that don't match your sample size?
Jamie actually implemented that. We were talking about that because I'm going through how you do this manually, and of course the next step is we want to automate this so you don't have to do it manually. But if you don't know how to do it manually, and in particular if the software developers don't know how to do it manually, it's hard to automate it. But when we were doing that, are you going to talk about that or not?
If we have time, or I'll do it tomorrow morning.
Yeah, it's like newer code that we're just coding up in version 22, but we do have the option to ignore these below a specified frequency. Because you see these coming up with like weird damping values, and it's just not real.
You mean
Yeah, so now this is an important point to get. We analyzed now 3 signals, and we found that there were 4 modes. Each of these modes exists to some extent in each of the signals. So to reproduce each individual signal, we're going to use these modes with this damping, and then there's a value that says how much does that mode manifest in signal 1? How much does it manifest in signal 2, in signal 3? Okay. So we could again look at the signal dialog for each signal. So if I go to signal 3, I can go there, show signal dialog, do what I did before. I want to plot them, and I've got my color I don't like.
want, I'll send Jamie an email to remove that color.
Jamie knows. It's some automatic component or something, right, that they, I don't know how they
No,
select
I
this
think
color.
that's, that was probably you or me 20 years ago.
I think it's you.
I can guess who it was.
Anyways, you can see we matched it pretty well. Okay, we matched it pretty well. I could go to another signal, let's say signal 1, and do the same thing, and show signal dialog, and look at that, and plot it out, and I won't change the colors here, but we match signal 1 pretty well too. We're using the same 4 modes, they just manifest with different complex numbers in each one of those modes. And those complex numbers are a magnitude and an angle. Okay, so that's looking at the individual signals. What we have here, going back to the main form, is if you scroll over to the edge, the right edge, there's a value called the cost function. The cost function quantifies how closely we're matching each signal. So it becomes a way of quantifying how close you match each signal. And usually only the relative values are important there, but we'll talk about that more going forward. But this is used to quantify how well we match. Okay, and lower means a better match. If it were perfect, the cost function would be 0, but we're seldom going to get 0. Okay, so everybody okay with that? The other way we could look at it, and we could say, okay, for this 2 Hertz mode, it had damping of 11%. This is a largest weighted percentage for the mode, 25%, and it manifested in generator 3's speed. So this is now saying for each mode, what is the mode and damping? That's common to all. What is the largest value, and what signal has the largest value? If you want to know the details, you just right-click on that entry and do show dialog, and this says for each signal in this mode, the 2.05 Hertz mode, what was the unscaled magnitude and what was the angle of how that signal represented in that mode. And some of these values will be high, some will be low. What this is saying is that signal 1 and 3 were manifested in that mode, whereas 2 was not. So the way to interpret this mode is to say this 2 Hertz mode is generator 1 oscillating against generator 3. Okay. If we look at the 1.65, the way to look at it is to say pretty much all the generators participated, 2 participated the most. Now if we look at the angle, there's a 10 degrees, 4 degrees, minus 170 degrees. This is saying this is generator 1 or 2 oscillating against 1 and 3. Okay, so now we know how each of our generators participated in each of the modes. How they participated is given by a complex number. It's got a magnitude and it's got an angle. If 2 things are oscillating against each other, they're going to be out of phase by 180 degrees. Okay. You might say, is this total magic? And I'd say, no, it's not total magic. There's actually an algorithm behind it. The technique is based on something known as the matrix pencil method. This is a newer technique for determining modes from noisy signals. It dates from about 1990. It was introduced to power system problems in 2005. It's an alternative to the Prony method that goes back to 1795, introduced into power in 1990. So, you know, this is, signal analysis is a general field. There's signals everywhere. People are developing these newer techniques This is a newer technique that was developed. If you went to school like I did before 1990, you didn't hear about the matrix pencil method. I didn't hear about it until maybe like 7, 8 years ago. But it's a way to take a sampled signal and get its modes. And just as you form something called the Hankel matrix, which is if you have m samples, the size of the matrix is m over 2, and you just kind of divide your samples up here in this way, it just becomes a matrix. It's very easy to form. Then you calculate the matrix singular values using economy mode singular value decomposition. Then when you do a singular value decomposition, how many of you know about singular value decompositions? Really? Okay. I shouldn't say really,
I know what
because
it is.
honestly, I did not know about singular value decompositions until I started getting into this stuff. A singular value decomposition, which like I said, I hadn't heard about 10 years ago, is a very common matrix analysis technique. How many of you know about image compression? Okay, image compression is using singular value decompositions. All this facial recognition and stuff is based on singular value decompositions of matrices. When you do a singular value decomposition, which is a standard mathematical technique that we've coded in Power World, you're basically taking a matrix and breaking it down into values that are known as singular values. They tell how much information is in the matrix in kind of an interesting way. When doing this, we take the largest singular values and get rid of the smaller ones. And I'll show you an example of this in just a second. This is an aside. It just goes through a little bit of SVD. It's not a new concept. It goes back 100 years, but it's found lots and lots and lots of recent applications. So we're teaching it now more in school. Here's an example of representing a matrix using singular values. This is an image, and this is the original image. You can think of that image as a matrix. I think it's a 250 by 250 matrix. So just a pixel value here, it's a black and white, so it's just what's the color of that pixel. So think of it as 256 by 256. Okay, so I've got a 256 by 256 matrix. If I did a singular value decomposition on it, I'm breaking that matrix up. And what you do is, if I were to look at the first singular value, the largest one, and I would take a vector, there's two vectors associated with that decomposition, and reproduce the matrix using one singular value, that's what it looks like. So I've taken that 256 by 256. That requires that I store 256 squared pixels. If I take one value and two vectors, which are 256 each, now I'm just storing, in essence, 2 times 256, 1/28 of the information. I get something that looks like that, and that doesn't look that good. But if I do 2 of them, 3 of them, 4 of them, this is 6, 8, 10, 12, eventually you've got it pretty well. And this is the basis of image compression. And it's all, I mean, there's all these algorithms that are doing it. It's also the basis of facial recognition, because when I see your picture, I do a singular value decomposition on it. I've got singular values and eigenvectors, and if I see those same ones, I'm Facebook and I say, oh, there you are. And you might be, changing your expression and stuff, but the essence of who you are stays the same. So this is how all this stuff works. It's a very common technique.
I didn't know my brain was that smart.
Yeah, brains are pretty smart.
So even if I scowl a lot, it'll still find me?
It depends on the algorithm, I don't know. It's like, I don't do that stuff, but we're using singular value decompositions all over, and they're coming into power all over the place. This continues on with the algorithm details. You form these matrices. You get discrete time poles on them. From those, you can get the eigenvalues. Once you get the eigenvalues, then you get the damping on your modes. So that's what we're doing. The matrix pencil method can be augmented by many signals. So we start out with this Y matrix for one signal. If I want to do n signals, I just stack the matrices up. And I have to do a singular value decomposition on each of them. A singular value decomposition, in essence, the time is, it's on the order of the number of rows, column squared times the rows. And how big the matrix is depends on the number of samples. So the takeaway on all these algorithms is if you sample more often, you're going to take more time, and it's going to go up with the cube of the number of samples. And it goes up linearly with the number of signals that you want to consider. So that's a nice part, is it goes up linearly with the number of signals. The bad part is it goes up with the cube of the number of sample points. So when we say, what's the highest frequency that you want, if you say 5 hertz, great. If you say 10 hertz, then it's going to take us 8 times as long to do it. It goes up with the cube. Okay. A good insight that came out of some work with, work that we've been doing recently is when dealing with mini signals, usually the signals are somewhat correlated, so very few of the signals actually need to be included to determine the desired modes. Ultimately, we want to know what modes are in our set of signals. The alpha value is found using the matrix pencil method and is common to all the signals. The B vector is signal specific. The good thing about the B vector is we can calculate that super fast. This is an insight that we got from the paper by Alex Borden and Bernie Lasser and Jim Gronquist from 2013. It basically gave us a really quick way to calculate the B vector. So we can do singular value decomposition on a few signals and then see how well many signals map into those modes. That is lickety fast. And what we do is we use something called a pseudo inverse of a matrix. How many of you know about an inverse of a matrix? Like everybody. How many of you know about a pseudo inverse of a matrix? Jamie,
I haven't gone into your code yet. It is all magic to me right now.
Yeah.
I'm building a wrapper around it, but I've not gone in there.
Yeah, the pseudo inverse of the matrix. I hadn't heard about it before I got into this about 8 years ago as well. A pseudo inverse of a matrix it generalizes the concept of a matrix inverse. A matrix inverse exists for a square matrix. Pseudo inverses generalize this to any size matrix, be it m by n. And there's specifically a Moore-Penrose matrix inverse. There's algorithms to do this. The calculating a pseudo inverse of a matrix actually requires that you do a singular value decomposition, which can work on any size matrix. These are some slides that I won't go through, but a nice thing about a pseudo inverse is this: it allows you to solve the least squares problem directly, which you may have run into the least squares problem where, for example, say you want to fit 3 data points to a line. You're solving a least squares problem. If you get a pseudo inverse, and the example goes through how to do that, I won't delve into the details here, but then you can directly solve it. What we do is we use the pseudo inverse to calculate the B vector for each signal, and we can do it super fast, and that is a key insight, is we can quickly calculate these B vectors. So to show you what this does for you, we're going to talk about something called the iterative matrix pencil method. When there's a large number of signals, we use an approach called the iterative matrix pencil to figure out which signals we should use in calculating our alpha values. And probably the best way to do this is to just do an example. So let's open up our 2000 bus case. So in that directory there's a case called, it's ECEN 460 TSGC underscore gen drop. So go ahead and open that one up. We had an ARPA-E project where ARPA-E wanted us to make up synthetic electric grids. Synthetic electric grids are just fictional electric grids that have the same complexity as actual electric grids. And we've made up synthetic grids that cover all the continental US for this project. Here, if we put them all together, we have an 85,000 bus case. Okay, so that's pretty big. We're just going to look at Texas, which is a 2,000 bus case. So this looks like Texas, but it's not the Texas grid. It's a fake grid. The nice thing about having a fake grid is we can give it out to people, we can put it online, we can use it in our classes. So the ECN 460 is our undergrad class. We use this case with our undergrads at Texas A&M. They love it because they're all from Texas, and they'll say, hey, that's my town there. So they like that. But in our case, we're just going to do transient stability on it. So click on the transient stability, and I've got the transient stability set up to run a gen drop of the two largest units in the case. I'm going to drop 2 units at time t equals 1 second. We're going to run it for 15 seconds. The nice thing about the 2000 bus case is it runs in about real time. So if you click the run transient stability button, you should get your results pretty fast. And that's just the frequency response on the system. Everybody getting this? Okay, and if you know much about systems, you're kind of looking at the oscillations there, saying maybe they need a few more stabilizers in there. Somebody has to design the stabilizers on the system. The graph here shows some voltage magnitudes. If you go to bus frequency all, these are all the bus frequencies at 2,000 buses, all the bus voltages, and the bus frequency at 10 selected buses. Okay, we're going to do modal analysis on this. So if you go to add-on modal analysis, I think it already has the bus data loaded up for the 2000 signals. If you want to reload it, you could go up to data source from plot and pick the plot as being bus frequency all, and then say just load signals, and it will load the data from the plot. Or you just keep what was there. Okay? If you scroll down here, you'll verify that we've got 2,000 signals. And each one of these signals is a bus frequency. What I told you is the matrix pencil method scales with the cube of the number of time points and linearly with the number of signals. If you have 2,000 signals, it would take quite a bit of time. So we've got it set to include all the signals. You shouldn't do that, but let's say you do it. So you click do modal analysis. We have a little box that pops up that says the number of included signals and or time points is excessive. Decrease one or both values. Okay. So it says don't do that. Okay. So let's first of all look at one frequency. So take the include column here and toggle them all to no, which you can do easily by right-clicking and set toggle column, toggle all no, and then include 1, and then click do modal analysis. It's automatically set your start time to be 1 there, which is the time where the last event occurred. It's going to end at 15, maximum hertz is 5, so we should be okay. So just click the do modal analysis. It does the modal analysis, and it reproduces this mode, or this signal, using 6 modes. Okay. So let's look at how well it did. Again, right-click on the first entry, do the show signal dialog. Well, before you do that, I should say, if you do the show linked object dialog, that will show the bus information dialog. That only works if there's a link between that signal and some model element. When you load data from the plots or from the transient stability results, that obviously exists. That won't exist if you just took a ComTrade file and loaded it up. So we try to give you access to this in case you want to know, hey, what bus is this? Okay, so do the second one, which is show signal dialog. Again, I'm going to do my comparison between the two to show you how well it looked by set toggle columns, plot column, changing the colors. And there's my reproduced signal and my actual signal. This dark one is the original value, the red is the reproduced value. Okay? Everybody okay with this? All right. But you might say, well, that's your best. What about the other ones? You've got 2,000 signals here. You just showed us the best. All right, which I did. So let's go back here, and this is the cost function which says how well did the signals match. Sort on the cost function. So click on the top of it there, and if you click once you get the best to the worst. If you click the other way you get the worst to the best. Okay. This one here is the worst. So let's see how bad is bad. So right click on that signal and show signal dialog, compare the original and the reproduced value. Again, I'm going to plot them and change my color. And you might look at that and say, aha, that's not that good.
It's the worst.
All right, it's the worst one. But you might look and say, yeah, look, you're not doing a good job of reproducing that worst one. So what would you do?
Toggle the signal for that column to yes.
Right, that's what you would do, is you would toggle that. You'd have to remember what column it is. That's the problem. But yeah, so let me, before you rerun it, you better keep track of which one. It's the easy name. It's comfort, bus point comfort 2-3. So I'm going to toggle it to include. So now I'm including 2 signals. Rerun it. Okay. Do modal analysis. Rerun it. And now it's got a total of 9 modes in it. We could either look at the worst again, or you could look at bus comfort 2, whatever it was. I should have set this up by numbers. It's a little easier, but I think I can find it. What was it called? Bus comfort?
I got point.
Oh yeah, point comfort. Was it point comfort? Did anybody find it? Bus point
Well,
comfort?
I sorted by include, so.
Oh, yeah, you made it too easy. Sorry, yeah. Okay, sort on include, that's a better way. Okay, so now its cost function is much lower, of course, and now if you look at it, show signal dialog, compare them. I know it's going to be low because I know the cost function value is low. And I'd be like, hey, look at that. Now I've matched 2. And you might be like, well, that's 2 out of 2,000.
How did you do the, so you just have to say, include yes for that bus? Is that how you got that extra signal in there?
Yeah, I clicked the include the yes. Some of us were smart enough to sort by that afterwards to look at the results. And
It then occurred to Tom to automate this, which he's about to get to.
right, so then it occurred to us and said, oh, this is like a good process, maybe we should automate this. So we would sort it again by, you'd look and say, well, what's the new worst? And I'm going to include that new worst. We thought this is like an iterative algorithm. So we called it the iterative matrix pencil method. And then we looked and we said, how many signals do we have to include? And it turns out with frequencies, because they're pretty well correlated, you only have to include about 10. So if you change the calculation method from matrix pencil to the iterative matrix pencil method and click the do modal analysis, with iterative matrix pencil, it just automates this. It picks one signal to include, then it looks at the worst, it includes that one, it looks at the worst, it includes that one. And it does it so many times, and it's up to, let's just say 10. Click on that, and you can see it processing there. Signal 6, 7, 8, 9, 10, and it got a total of 11 modes. If you click on the cost function and sort, now the worst cost function is actually really pretty good. And if you don't believe me, you can, well, let me just show you. You can look at the worst signal and show it and do the same thing as before. Change the cyan to something better. And that's the worst. And it's like, that's not bad. And we have now reproduced all 2,000 signals. Okay. And we did it here during a demo. And on each one of these modes, we know the largest percentage. So I can look and I can say, okay, and I know the damping on each one of the modes. Let's sort on damping. The worst damping here is 6% on the 0.6 hertz mode. Okay, so now let's dive into the 0.6 hertz mode. So if you want to dive into it, just right click on that and do show dialog. It shows for this mode, it shows the magnitude and angle of how each one of our signals is that mode manifests in each one of our signals. And we've got that now. Okay. And I did this all while standing up here, and you all did it too. So are there any questions so far?
So in your example, is then, would you look at the magnitude to find where your problem is? So like, is Brownsville the issue?
Okay, this gets into a broader issue, which we're gonna dive into in the slides, and that's saying, why did you wanna do this, okay? Well, what I have told you is, on all 2,000 signals, what are the modes and the damping, and that's something that you might wanna know, okay? As a planner, then you might say, how do I increase the damping on that mode? And that's a different question. Okay, but you know what that mode is. And I'm gonna show you how to visualize that mode in just a second. But you know, you might, of course this is a fictional system, but if this is a real system, you might say, well, should I put more stabilizers in there, things like that. That's where you have planning engineers figure that stuff out for you. But at least we have taken the data and we've calculated what the modes and dampings are. Where we're going with this, and now that Jamie's actually interested in this, he's automating it. Because naturally you'd want to say, okay, you can do this pretty well. Can you do it well enough that you can automate it? So I just did a transient stability run. I don't have time to go through all this on all my runs. So can you do this for me automatically and say, hey, your worst mode is, your worst damping is 4%, and that quantifies that run. Because you know, the damping's going to change as you put different events on this system. Maybe you're taking lines out or different operating points. So at least we can quantify it for you.
Yeah, one of the things that can be an educational piece for me, I think most of our customers, they want to know what is the damping of this signal. And that's not what you're telling them. We're telling them it's made up of these components, all of which have their own damping. And so that's going to be something that kind of you have to wrap your heads around.
Right.
It's not what you were thinking you were asking, I guess.
Yeah, I mean, if we look at, you know, one signal here,
And every signal is made up of all of these.
you know, yeah, I mean, you get this signal and you say, what is the damping of that signal? What I would say is that signal's made up of a bunch of signals. And I can tell you for this particular signal how it manifests in each of the modes. And it's pretty clear that there's some dominant mode here. And if we looked at this particular signal, these are the modal results for that particular signal. I've been looking at the original reproduced. If I just go over the modal results, this says for that signal, there's this frequency mode with this damping, and this is saying how much it contributes to the signal. This one here is the biggest contributor to that signal. You know, I just sort by either, we show the magnitude either scaled by the standard deviation or unscaled. You can sort on either one, and you get a feel for that signal. And if you said, what's the damping on that signal, I would say, okay, the largest oscillatory component in that signal is at 0.8 hertz, and it's got a value of unscaled 0.436. Okay, and then I'd say, oh, and there's another component that's at 0.3 hertz, and it's got a magnitude here. And then I show you the real and the reproduce to quantify it until, like, you know, that you feel good about my results. You feel like, yeah, this is right. Okay, I'm demonstrating that we've matched pretty well. And it's not saying we can match any signal, because if that signal ultimately is not made up of exponentially damped sinusoidals, you're not going to match it that well. And we saw that at the beginning where we tried to take that signal that was flat and then changed. We just didn't do a good job on it. Okay, so this is a quantification, and you know, kind of what it goes well beyond is somebody taking a piece of graph paper or a JPEG and trying to figure out, you know, how did the peaks change. That's simply automated. But the signals are complex. They're not just one mode. There's different modes in there. Okay. So going back to looking at our system with the 0.6 hertz mode, and you're saying, okay, what does that mode look like? If I took each one of those 2,000 bus locations that are a component of that mode, they have a magnitude and an angle, and visualize them, it would look like this. And you might say that's a lot of arrows. So what we do is we have a way of pruning arrows, and then we color them based on the direction. But this is a mode in our Texas 2000 case that is sort of like the system oscillating around. Okay, it sort of like circulates around. We have a WCC equivalent, not equivalent, synthetic grid that we built using a 765 kV transmission system, and that one in the west also kind of has this oscillation spinning around to it. We can do this, of course, with real systems too, and we've looked at the different modes in the WCC, and we can easily visualize those modes. All of this was based upon data that we got from a simulation, but it was ultimately driven by the data. Once you run the simulation, you have the data, there's no model that goes into this. It's just driven by the raw data. Okay?
Basically what's happening is if you take out one end, it's going to just reverberate throughout the rest of the system. Kind of what Eric did.
Yeah, so the question for the planners is saying, does having this help you out? Does being able to see it that way help you out?
Looks cool.
Yeah, it looks cool. I mean, so it's sort of saying, I mean, if somebody said damp that mode, and I might say that to my students, I said, yeah, you guys know how to design stabilizers because they've taken the class that we'll talk about tomorrow. Damp that mode. And you have to put in a bunch of stabilizers to damp that mode. You know, so you tune your stabilizers to the 0.6 hertz mode, and then you'd figure out how many do I need, what do I want to do with them. You know, you're not going to do much in this part of the system with damping that because it's sort of oscillating around there. But if you're up here or down there, you might be able to do something with it. So it's giving you insight into the problem. And of course, in WCC, you guys know the different modes you have. But you know, if you have a severe contingency, those modes could switch around. This is something that could tell you how those modes are switching around based on actual data, like PMU data, and you can visualize it as well.
Tom,
Yes?
so with a plot line or a graphic like this and where those arrows are the relative direction, is that basically saying, you know, the north end of Texas is oscillating against the southern Rio Grande Valley?
It's basically saying it's circulating around.
Okay.
Let me show you something, and the slides here now talk about how to visualize stuff using, so we talked about getting mode details. The next couple slides, which I'll go through and we'll still be done by 4:30, say how can you quickly visualize information when you've got geographic data associated with your information. And the good thing about the synthetic grids is we have every point in the grid geomapped. You guys now have all your substations geomapped so that you can do this as well. And we do this with the actual grid as well. GDVs, or Geographic Data Views, were introduced in PowerWorld about 12 years back to provide a quick way of visualizing information about the grid, and they're ideally suited for modal results. To create a GDV1 line of the substations, we just go to Case Information Aggregation Substations, right-click on any column and select the Geographic View, select column, then Geographic Data View. Okay, so I read that pretty fast, but let's do it. So in this case, close the modal stuff, close the transient stability, just go to case information, aggregation, substations, and that shows a list of all the substations in the case. I'm not showing it to you, but every substation has a lat longe associated with it. Let's say I want to quickly visualize what's the source of my generation. So if you right-click on the gen column and go down to Geographic Data View, which is right there, then you'll get a sub-menu that says Select Column, then Geographic Data View. It will call up the Geographic Data View display. And you can do this on a subset of the data in a case. The starting point for this is you need to have a one line. We're going to put objects on a one line automatically. So the starting point is to open one lines with map projections. I've got some already defined, but let's browse to open an existing one line. So click on that. I gave you a blank one line in North America. It's just North America blank right there. Click on that. Click open. And then there's a whole bunch of different options for how your GDVs appear. For right now, just click the bottom option and say Add Geographic Data View Objects. And what that does is it pops on the one line objects that can be dynamically sized for every substation in the case. Y'all got that? If you go to any one of these objects, like you can scroll in and say you right click on it, you can either look at its substation information dialog, you know, there's whatever substation that is, or you can go to the GDV display and customize it. And one way to customize it, you guys following? One way to customize it is to go fields and attributes, and this provides a lot of customizations for how the display appears. The good thing about GDVs is once you do this once, you have them forever, because they're ultimately a Power World PWD file that's linked to this case, but it can be used with any case with the same substations. Say I want to scale the total area by the output of the generator. So if you click on total area here, it's already selected the dynamic field to be the generator megawatt. That came from the fact that we clicked on the megawatt value originally. So if you click here, it's going to scale the size of the symbol on the one line according to this function right here, and if you change the characteristic value, you change how big they appear on the one line. And the field value is saying if the generator's output is 0, make it size 100. If it's 4,000, make it size 100. There's you just kind of have to guess on how big to make these things. But I might say if I got a generator with 0 megawatt output, I want it to not appear. And if I've got it with 4,000 megawatts, let's say I pick it to be 5,000. Then I click OK, and now I have a display where the size of the symbols is dynamically sized based on the generator megawatt output. Okay, you could save that and use it later on. Okay, these are GDVs. We've had them for a long time, but as we've gotten more cases that have latitude and longitude info in them, they're more useful. just for fun, if you go to the geographic data view options again, and you click over here to Pseudo Geographic Mosaic Display, click Apply and Update Mosaic View. This is a way to visualize the information in a way that you can read it. And if you click back to restore, they go back to where they were. That's like a new feature that we think is kind of cool. But you know, you have these and it's like it's hard to see where they're at, but they're pseudo-geographic because they kind of map into rectangular space based upon where they are in geography. If you want to get sick to your stomach, what you do is there's ways that you can make up the animated, what are they, GIFs? The animated displays that are going in and out and in and out, and they get you nauseous after a while. But it's available anytime you want, you can do that. It's under the Pseudo Geographic Mosaic Display, just to click Apply, and it will apply, and there's a bunch of options. These are all dynamically linked, so if you want to look at the Willis substation, you can look at it.
Does it plot the, or can you plot the tie lines between the substations?
We haven't yet done that. There's all sorts of stuff that, if people get interested in this, there's lots of cool stuff that we can do. If I'm going to go back to the View Geographic Data view, and first of all unapply it. So I'm going to restore. And then if you look here under general display options, we're showing rectangles. You can show rounded rectangles, ovals, triangles, kites, arrows, and line segments. It wouldn't make sense to represent a substation with a line segment, but it would make sense to represent some things with line segments, like lines. So this is something that we're adding. We're still kind of under development on it. But there's a lot of functionality here. Okay. So that's that. That's that. We went through that. Transient stability toolbar. A lot of times when you run a simulation, you might want to visualize the results. And we saw that with the movie that I showed of the double Palo Verde fault, how you saw the frequency variation. Now that we've got a GDV display, we can visualize it using the GDV display. So I'm going to demonstrate using the toolbars and visualizing them using a GDV display. This is a GDV I created. It's ECN 460 _ small sub. It's just this display where I make all the substations really tiny so they don't appear. I just want them so I can contour stuff. So what we're going to do is go to add-ons, transient stability case info, do show transient contour toolbar. Have you guys used the transient stability contour toolbar? It's something that Jamie put in and it doesn't get out too much, but it's really cool. If you want to visualize the results, there's really cool things you can do with it. Close this one line, you don't have to save it. Close that display, and then open up, close this one, open up the one line, it's the small sub, so it's ECEN 460 small sub. So just open that one up.
Sub small.
Or sub small, sorry.
That's not your fault. I do the same thing.
Yeah, okay. So, yeah. This is essentially the GDV that we made earlier. I just saved it. Okay. Now, in our transient stability results, we saved the bus frequency, but we also saved the substation frequency. When I set up the case, I did that. The transient stability result, or I'm sorry, the contour toolbar lets you visualize results in a contour sense. So we're going to select a device type. We're going to show the substation frequency. So for device type, select substation. And then for the field, select the top one, which is TS frequency average. Okay, so this should be substation, this should be TS frequency average. Then go to the options, and we're going to put a contour on this. So if you go to the options, the top one is contour. I defined a contour. The object type you can't change here. Pick a color mapping. I've got a discrete 15 red blue on it. For a maximum, put 60.25 hertz. For a nominal, pick 60, and for a minimum, pick 59.75.
I didn't catch how you opened that dialog.
Okay. Okay, it's down here under options. Oh, the toolbar. The toolbar was under add-ons. Yeah, the toolbar itself is add-ons. Transient stability case info, show the contour toolbar. And then once you've got it, go to options, contour options. Okay. And then I specified my contour as 60.25, 60, and 59.75. There's an option called export, which we're not going to do, but if you select export, as you're doing this, it'll make a bunch of JPEGs. You can string those JPEGs together to produce a movie. So once you've got this, just click the play button here, and what it's going to do is it's going to go through sequentially your transient stability results, picking whatever increment you decide from the present time, or the start time to the end time, and create a contour. And we'll see it kind of playing in real time here. These are all JPEGs that can be saved and strung together in a movie. So just click that. And what you'll see is our disturbance, which occurs at time t equals 1.
Are you plotting frequency right now?
I'm plotting frequency right now. I'm plotting the results that we stored.
Basically, what it's like, imagine you're taking the plot, but instead of putting the numbers on a little spoon plot, we're just sending it out to the diagram, contouring it as we go.
Yeah.
That's basically what's.
Yeah, this is, I showed you that first movie that I made by going step by step by step. Running it, pausing it, saving a JPEG. This automates all that. So you can make movies up really easily with this.
Yeah, after you play with this for a couple weeks, you're gonna eventually call and ask a question, and the answer will be disappointing to you. Because a lot of people are like, "Oh, this is cool. I can just do contour right through, and simulator will bring over all the generator outputs, all the line flows, all the voltages, all the frequencies at each time step." It's like, no, we're not doing that. All I'm doing is bringing over the one value that's your contour. So if I were to zoom in here and look at a voltage, it would not be changing.
Can this be an expression?
No.
Well, I'm already disappointed, thanks.
It's like really cool, but it's not, I mean, if you want to animate everything, you have to kind of just pass it over during the simulation.
Yeah, the more we do, the more there is to do. But,
Exactly.
you know, the idea is that you can make a movie like this, and you could do it on voltage, magnitude, or whatever you can save. You can make a movie of the contour of it. So, we said we'd be done by 4:30, and it looks like we have 17 seconds left, so I will finish this up right at the beginning tomorrow.
And I'll show that we're creating a new object in version 22 called a time window, where you kind of define ahead of time these kind of modal calculations. I told Tom we cannot have a default dialog in simulator that has the word matrix pencil on it. But he always says, why not? Everyone knows what that is.
We